This program is about the physical oceanography of Long Island Sound, how the water circulates, and what makes it flow the way it does. There are two major types of currents that we'll learn about, the tidal currents and what are known as the non-tidal currents. These currents are constantly interacting in the Sound. The more we learn about them, the more we'll discover how this water actually moves in Long Island Sound. And knowing this, we will be better able to protect its health today and in the future.
Headed up into the waves.
Sally Friedman is about to swim from Montauk Point, the eastern tip of Long Island's South Fork, to Rhode Island. By plane, the distance is just under 20 miles. However, Sally must swim much further than this to reach her destination. This is because of the various currents and tides at work here, which will push and pull her as she swims. Her course will take her just seaward of the eastern opening of Long Island Sound, called the Race. Here the Sound exchanges large volumes of water every minute with Block Island Sound and the Atlantic Ocean. The current can reach 5 knots through the Race. This is a considerable current to contend with when swimming at a rate of about 2 knots. A knot is equal to 1 nautical mile per hour, which is slightly greater than 1 statute or land mile an hour. Swim strategist Tim Johnson.
We planned this swim out. What we initially planned was for Sally to swim a half-mile east, head north on a current, past Shagwan Reef, go by this shoal whistle, and head for the center of Fisher's Island, and then slip down the backside of Fisher's Island, and then do a dash across here to Watch Hill Point while the current comes out on it.
Go, Sal! Yay!
Yay, Sally!
Throughout this program, we'll be checking in on Sally's progress. We'll see how well she does swimming in the constantly moving waters just outside the mouth of Long Island Sound. On the sandy shore of Long Island Sound, where now we see waves and water, in a few hours we may only see sand, rocks, and waterborne debris. This is because on the outgoing or ebb tide, the waters of Long Island Sound retreat from the shoreline. On the incoming or flood tide, the waters rise and advance up the shoreline. This ebb and flow of the seas is caused by the mutual gravitational attraction of the Earth, Moon, and Sun. The Earth and the Moon rotate in tandem through space, much like a baton being spun into the air. On one end is the Moon, on the other, the Earth. Gravitational and centrifugal forces form the connection between them. The gravitational force of the Moon pulls a bulge, marked here in blue, of the Earth's ocean toward itself as it travels its orbit around the planet. The Sun exerts a similar but weaker force. Another bulge of water exists on the opposite side of the Earth from the Moon. This bulge is caused by the centrifugal force created by the baton-like motion of the two spheres. On the opposite side of the Earth from the Moon, the centrifugal force is greater than the Moon's gravitational pull. The Moon revolves around the Earth once a month. The Earth rotates on its axis once a day. So, as a fixed location on the Earth, such as Long Island Sound, marked here by this orange square, rotates through these two bulges of water, that place will experience two high tides and two low tides. How these gravitational and centrifugal forces affect the tides in the Atlantic Ocean is particularly important to the movement of water in Long Island Sound. This curved line marks the progression of the high tide as it travels down the eastern coast of the United States. A portion of this tidal wave enters Long Island Sound through the eastern opening of the sound, the Race. As the water flows into the sound, sea level rises and covers the shoreline. This side view image of Long Island Sound will illustrate the rising and falling tide starting from mean sea level at hour 0. At hour number 1, the water in Long Island Sound has risen to this level. At hour number 2, it has risen even higher. At hour number 3, the sound is at high tide. During the next 6 hours, the sea level of the sound drops as the water begins to exit the sound again through the Race to the ocean. At hour number 9, it is low tide in the sound. At this point, the rising tide in the Atlantic Ocean is beginning to pump water into the sound again. The level of the water in the sound rises accordingly. At precisely 12 hours and 24 minutes from the start time, the level of the sound reaches mean sea level once again. 12 hours and 24 minutes is precisely 1/2 of a lunar day. A lunar day is the time it takes for the Earth to complete one rotation under the Moon. So during half a lunar day, Long Island Sound has rotated through one of the bulges of water on the Earth. The character of the tidal wave is affected by the mean depth and the length of the sound, the shape of the shoreline, and the bottom features, such as the Mattatuck Sill. The amplitude, or height, of the tides in the sound is increased by a phenomenon known as resonance. Here is how it works. As we've just seen, the water pumped into the sound by the action of the oceanic tidal wave travels to the western end of the sound. It raises the level of the water here as it becomes restricted by the narrowing shorelines of Long Island and Westchester County. But then, like a wave in a bathtub, this surge of water reflects off the narrow end of the sound and begins traveling back toward the eastern opening again. As the tide in the sound starts ebbing, the level of the Atlantic Ocean begins to drop as well, so that the outgoing tide from the sound is synchronized with the outgoing tide in the ocean. Being synchronized with this cycle creates the phenomenon of resonance, which increases the height or amplitude of the wave in the sound. At the Race, the average range of the tide is 0.7 meters or 2.2 feet. The range of the tide is the difference in the depth of the water between high tide and low tide. The range of the tide in the Western Sound is 2.2 meters, or 7.3 feet, nearly 3.5 times as great as at the Race. The speed of the tidal current is also slower in the Western Sound than in the Eastern Sound. Through the Race, currents can reach up to 5 knots, whereas in the western sound, they're not likely to achieve over 1 knot in speed. The speed of the current is normally higher at the mouth of the water body than at its head. In the case of Long Island Sound, the current speed at the mouth is increased even more because all that water has to squeeze through the opening at the race. It's about 4 hours since Sally Friedman began her swim. At this point, she is approaching the channel called the Race.
Great. Okay, Sally, you've gone about 4 miles.
What?
You've gone about 4 miles. I'm going to go over and look at the charts on the big boat, and we might do a little swimming straight up to the race. We should be in that current that cuts across. But since it looks like we're maybe running a little behind, I'm going to want you swimming directly to the race. We got an hour and a quarter till the tide changes.
Because she is late, Sally is missing a golden opportunity to swim across the Race, that region of the Sound that experiences the strongest currents during what is known as slack water. Slack water is the short time interval lasting from about 1 hour before to 1 hour after both high and low tide. The current is at its weakest during slack water as the direction of the tidal currents are reversing and switch from an outgoing tide to an incoming tide, and vice versa. Swimming the Race during slack tide would save Sally time and effort, two precious commodities when one is trying to swim this distance in a single day.
Right now we are approximately here. We're about 2 miles out of position of where we would like to be. We got a little bit of a late start, and we're headed north right now, which we're probably aim for this point right now, and we'll have to see how that affects the finish of the swim.
As Sally continues to battle the currents on her swim, let's return to our investigation of the physical oceanography of Long Island Sound. Aboard the Onrust, the research vessel of the Marine Sciences Research Center at the University at Stony Brook, students will gather current data in order to study the movements of water in Long Island Sound. Using this current meter, our student scientists will measure the direction and speed of the currents at various depths.
Turns into a reading on the meter over there.
Out here in the middle of February. It's cold, slippery.
With the current meter lowered into the water from a winch, the readings are first taken at the surface level.
Floats horizontally there.
Then, the meter is slowly lowered down to 10 meters, and more data are recorded. The direction and speed of the current being measured are not only caused by the powerful motion of the tide, but also by the non-tidal currents.
We can record the currents at one location at different depths.
The non-tidal currents are the wind-driven current, the density-driven current, and the tidal residual current. Non-tidal currents help to form slow, persistent, long-term circulation patterns, which are usually obscured by the stronger and more obvious movement of the water caused by the tides. The tidal currents are relatively strong and move back and forth in the Sound twice in a day. The non-tidal currents are weaker. They can be thought of as being superimposed on the tidal currents to produce the observed circulation of the water at a given place and time in the Sound. The first of these non-tidal currents we will discuss is the wind-driven current. But let's first take a look at the most visible response of the Sound to the wind, waves. Although waves are the most visible response to the wind, waves contribute little to the motion of the Sound. In the Sound, during light winds, relatively small waves are formed which travel across the surface. Such local winds blowing directly on the surface of Long Island Sound are known as near-field winds. During the summer, near-field winds generally blow from the south and southwest. During the winter, from the north and northeast. During spring and fall, the winds tend to blow in varying directions. Waves caused by wind blowing across the surface of the water create a circular motion of the water. Let's watch how it works. Imagine that this ball floating on the surface is a molecule of water. As waves travel past the ball, they appear to move it along with them. But if we superimpose a circle on the ball, it is apparent that this water molecule is moving in a circle. Molecules of water at greater depths also move in circles, though their diameters are progressively smaller. So, although the water appears to be traveling from left to right, actually there is no net movement of water. There is, however, an exception to this. As waves travel into shallower waters, they become steeper until their crests fall forward as breakers. When the waves break, they do move the water forward up the beach, which can be important in forming the beach. There are 3 wind factors which cause wave conditions. These are the fetch of the wind, or the length of unobstructed waterway over which the wind travels; the duration, or the length of time that the wind has blown; and the speed of the wind, which is actually how fast the air is moving. Because Long Island Sound is almost entirely enclosed by land, the fetch of the wind is not very long. This is why the waves in Long Island Sound are small in comparison to the swell found on an ocean beach, such as Fire Island on the south shore of Long Island. In addition to causing waves which create very little water motion, winds can cause surface currents or large-scale storm surges. Local, near-field winds blowing directly on the Sound create a wind-driven circulation in the surface layers of water. Weather patterns which form in the northwest Atlantic Ocean and the Caribbean Sea or across the continental United States can also create wind-driven circulation in the Sound through the effects of far-field winds. During storms, these strong winds can lead to wind-driven currents, which may pile up massive volumes of water in what is known as a storm surge. Here's how it works. A hurricane moving up the eastern coast of the United States will drive water toward the seaward entrance of the Sound. The rise in sea level at the entrance to Long Island Sound produces a slope of water directed downward toward the west. This leads to a storm surge moving from the mouth of the Sound toward the western Sound. So near-field winds create small waves and weak wind-driven currents. Strong far-field winds create large waves and storm surges. Long Island Sound is an estuary, a semi-enclosed coastal body of water which contains a mixture of salt water from the ocean and fresh water from rivers. The major sources of fresh water to Long Island Sound are the rivers of Connecticut, the Housatonic, the Thames, and the Connecticut River. A portion of the fresh water from the Hudson River in New York mixes with salt water in New York Harbor and is introduced into the Western Sound through the East River. fresh water drains into Long Island Sound from a wide area, which includes portions of 5 states: Vermont, New Hampshire, Massachusetts, Connecticut, and New York. Fresh water enters the Sound from as far north as Canada. This area is called the Long Island Sound Drainage Basin. Here at the mouth of the Connecticut River, in the Eastern Sound, it is easy to see the interaction of fresh water from rivers and salt water from the ocean. This mixing of fresh and salt water leads to the density-driven circulation. It is also known as the estuarine circulation because a similar circulation pattern is found in all estuaries. Here's how it works. Fresh water has a lower density than salty seawater. It can be thought of as lighter than salty seawater because it contains very few salt molecules. The lighter, fresher water tends to float over heavier, salty seawater. Through the action of the tides, the mixing of fresh water and seawater leads to an increase in salinity with depth. The closer to the bottom, the higher the salinity. The salinity of the water is a measure of how much salt is contained in it. In addition to a higher salinity in the water near the bottom, the salinity of Long Island Sound water increases from west to east. This is because the eastern region of the Sound is closest to the Atlantic Ocean, which provides the greatest influx of salty seawater. These differences in salinity, and therefore density of the water, create the density-driven currents. The surface, or fresher layer of water, flows from the low salinity, western end of the estuary, toward the high salinity, eastern end of the estuary. However, the deeper water, which is saltier and heavier, flows in the opposite direction, from the east to the west, under the surface layer. We've now learned about the tidal circulation of Long Island Sound, the generation of wind-driven currents and storm surge waves, the generation of density-driven currents through the mixing of fresh and salt water. The final type of current we will discuss is known as the tidal residual current. The tidal residual current is the current produced by the tide as it is influenced by the unique shape of Long Island Sound. A point of land sticking out or a bay going in will create unique patterns of circulation as the tidal waves pass by them. But the most important feature of the Sound helping to create this tidal residual current is the shape of the bottom. A ridge on the bottom, such as the Mattituck Sill, or a deep hole, creates new flows of water as the tidal wave passes over them. This residual pattern of motion, caused by the tidal currents flowing over the bottom, reveals several important circulation features. Tidal residual currents set up a large-scale, counterclockwise motion around the perimeter of the Sound. The fresh water entering the Sound from the Connecticut coast also contributes to this motion. This perimeter current is important because it indicates that there is a significant exchange of water between the Long Island side of the Sound and the Connecticut side. A portion of this perimeter current is diverted by the submerged ridges and shoals in the Sound, including the Mattituck and Hempstead sills. These sills, acting as barriers, create smaller counterclockwise rotating eddies in the eastern, central, and western regions. Darkness is coming to Long Island Sound, and Sally Friedman is still in the water. For 10 hours now, she has been swimming, stroke after stroke, stopping only to be fed through bottles extended to her on a long pole. Now, however, she is finally approaching her destination, Rhode Island. Throughout her swim, Sally has battled all the various currents that flow in Long Island Sound. The current driven by the tides, the current caused by the wind, the current caused by the estuarine circulation, and the current caused by the tide passing over the bottom. All these circulation patterns overlap each other and create the complex motions which are moving and mixing the waters of Long Island Sound. Congratulations, Sally. Thanks to the aid of modern theories and computer models, scientists are able to predict with a greater degree of certainty just how and when the water will move in Long Island Sound. The results obtained with these tools are expected to have a significant effect on the management of the Sound. Being able to better predict the circulation of the water will help us to determine the movement of pollutants in the Sound. If sewage is discharged into Glen Cove Harbor, for example, where does it go? How much of it stays in the harbor? How much of it is moved into the larger Sound? Knowing the physical oceanography of Long Island Sound, we will be better able to protect its health for generations to come.